Hey class, today we're going to be doing section 5.20 in AP Stats, which is all about errors and hypothesis testing. So even if we conduct a hypothesis test correctly, we are still subject to the laws of sampling variability. So what that means is when we get a random sample, even if it's not biased, that random sample might not be a good representation of the population. That's just kind of one of the natural laws of randomness. We might get a bunch of samples that are great, and then we might get some that aren't. And when we have a sample that's not a good representation of the population, that could lead to incorrect conclusions for our hypothesis testing. So there's two possible incorrect conclusions. We have a type 1 error and a type 2 error. We do use Roman numerals for those. So the type 1 error is when the null hypothesis is true, but we mistakenly reject it. So the null hypothesis was true in reality, but we said, well, let's just reject it. The type 2 error is when the null hypothesis is false, but we fail to reject it. So these are the two possible errors. We have this nice little table here to help us remember. So for our hypothesis test decision, if we decide to reject H naught when H naught was true, that is a type 1 error. Now, if we decide to reject H naught when H naught is false, that's a good thing. This is a correct conclusion. Correct conclusion. And later we're going to talk about this is called the power of a test. Now, if we fail to reject H naught when H naught was true, this is a correct conclusion. So H naught was true. We failed to reject it. We did not reject it. That's good. And if we fail to reject H naught when H naught was actually false, this is our type 2 error. Now, we use alpha to denote the probability of making a type 1 error, and this is the same alpha as our significance level. And we use beta to denote the probability of making a type 2 error. So I have a nice little fun way to remember your two errors. Try not to get them mixed up. It's easy to get them mixed up. I just remember art is my BFF. So art, A for alpha, which is type 1 error, is reject H naught when H naught is true. So you can see that R, so the A for alpha, ART for art highlighted there. And then beta for type 2 is fail to reject when H naught is false. So the BFF is highlighted there. So kind of a nice way to remember. We learned so many things in AP Stats. It's hard to get everything to stick in our brains without getting all mixed up. All right, so let's look at example 1. We are conducting a hypothesis test with the following parameters. H naught is that mu is 98.6. Alternate, HA, is that mu is not equal to 98.6. A type 1 error would be concluding. So remember, type 1, so art, A-R-T. So we're going to reject the null when the null was actually true. So if I reject H naught, I'm going to conclude that mu does not equal 98.6, when in reality, H naught was true, mu did equal 98.6. And then type 2 error, BFF, beta, failed to reject. So if I fail to reject H naught, then I'm concluding that mu does equal 98.6, when in reality, H naught was false, so mu did not equal 98.6. All right, let's look at an example where we have a little bit more context, more things to talk about here. Water samples are taken from water used for cooling as it is being discharged from a power plant into a river. It has been determined that as long as the mean temperature of the discharged water is at most 150 degrees Fahrenheit, there will be no negative effects on the river's ecosystem. However, if the mean temperature of the discharged water is more than 150 degrees Fahrenheit, it will cost the government $5 million to modify the power plant. To investigate whether the plant is in compliance with regulations, 50 water samples will be taken at randomly selected times, so that's good, and the temperature of each sample will be recorded. So whether or not they ask you to identify the hypothesis, if they are asking you to talk about your errors, type 1 and type 2 errors for these problems, we definitely need to state our null and alternate hypotheses statements because it's all based on those. So we definitely want to state those. So H naught and HA. So remember, H naught or null hypothesis always includes the equality. So if I look at my two options, I have at most 150 degrees and I have more than 150 degrees. Well, at most means less than or equal to. So that's going to be the one that goes in the null hypothesis because it has the equal to in there. So this is going to be that mu is equal to 150 degrees Fahrenheit. We write equals, but really that's less than or equal to or at most. And then our alternate is that mu is greater than 150 degrees Fahrenheit. It's kind of nice to think about what the consequences or what would happen for each one of these. So if it's at most 150 degrees Fahrenheit, then government doesn't spend money, no negative effects on ecosystem. And then if mu is greater than 150 degrees, so if the water is more than 150 degrees, the government spends $5 million and there are negative effects on ecosystem. Okay. So now that I have my brain wrapped around this problem, I can talk about my errors. So describe a type 1 error in context. Now, when they ask us to describe the error, they're not asking you to describe the consequences of the error, just the error itself. So concluding that, so remember ART, type 1, alpha means reject the null when the null is true. So if I reject the null, I'm concluding that the true mean discharge temp is more than 150 degrees Fahrenheit, when in reality, the temperature was at most 150 degrees Fahrenheit. Now on the next page, they ask us, what are the consequences of this error? Well, if we conclude that the water temperature is more than 150 degrees, what does that mean that's going to have to happen? Well, the government's going to have to pay $5 million to fix the power plant when really the temperature was fine and they shouldn't have had to do that. So the consequence of the type 1 error is the government will unnecessarily spend $5 million on the power plant. So unnecessarily is that, well, they didn't really have to, but they had to, because that's what the error we made in our calculations. Well, okay, let me explain. We didn't make an error in our calculations. It's just based on sampling variability. Our sample must not have been good representation of the population, and that just happens sometimes. Not great when it happens, but it does happen sometimes. All right, so now type 2 errors, remember BFF. So our type 2 error would be concluding, so we're going to fail to reject the null when the null was false, concluding that the true mean discharge temperature, if we fail to reject it, then we're concluding that it's at most 150 degrees Fahrenheit, when in fact the temperature was actually more than 150 degrees Fahrenheit. Now, personally, I think that this is a worse error. The consequence of making this error, so we concluded that the water temperature was fine when in reality it wasn't. It means that the necessary power plant upgrades are not made and the river's ecosystem will be damaged. I love the earth, so this makes me sad. Which error would you consider to be more serious? Explain. So these types of problems, sometimes, a lot of the time, it depends on perspective. Sometimes it doesn't. There's definitely one right answer, one wrong answer sometimes. But in this context, I mean, it kind of just depends on your perspective. If you were thinking about the perspective of the government official, well, they might think that the type 1 error was worse because they ended up having to spend $5 million when they shouldn't have had to do that. If you're someone who loves the earth, then maybe you'll think that the type 2 error is worse. That's where I am really. So I think that a type 2 error would be more serious because the river's ecosystem will cost a lot of money to repair, or it could be permanently damaged. So if it's one of those problems that depends on perspective, just choose one direction, whatever you think, and make sure to justify it with your with your context. All right, now if you're in my class, there's 2 examples coming up next that we're actually going to skip. So go back to the calendar later and copy those in. We're going to go to this page and talk about power of a test. So I mentioned power of a test on page 1 when we did this table. Power of a test is rejecting the null hypothesis when the null was false. It's a good thing. It's a correct conclusion. So power of a test, when the null hypothesis is actually false, we hope our test will lead to the correct conclusion of rejecting our null hypothesis. The power of the test is the probability that the test correctly rejects a false null hypothesis. So it's a good thing. It's not an error. How do we mathematically find the power of a test? Well, if the power of a test is rejecting a false null hypothesis, then the complement is failing to reject the false null hypothesis, which is a type 2 error. So we can find the power of a test by doing 1 minus beta, which is the probability of a type 2 error. Now, there are certain things we can do to impact the probability of making that correct decision, the power of a test. I can increase the sample size. So the larger the sample size, the more likely a false H0 will be detected. Therefore, larger the sample size, the greater the power of a test. So having larger sample size is always a good idea. The effect size. So the effect size of a test is the difference between the true value of the population parameter and the hypothesized value. The greater the effect size, the more likely a false H0 will be detected. Therefore, the larger the effect size, the greater the power of a test. So just to kind of visualize this a little bit here, if this was our H0 like p-value, and I had a p-hat value that was kind of close to H0, and let's say my alpha was here at 0.05, I would fail to reject this. But if I increase the effect size, if I, hold on, sorry. Okay, if I increase as my p-hat gets farther away, so as we increase that difference between the true value of the population parameter and the hypothesized value, I'm more likely to land in this zone where we would reject our null hypothesis. And if the null hypothesis is false, that's a good thing. We want to detect that false null hypothesis. So the larger that effect size, the farther away it is from the true value, the greater the power of a test. All right, we can also increase our power of a test by increasing our alpha level. So increasing alpha makes it more likely you'll reject H0 since the threshold of being statistically significant is easier to achieve. So increasing the significance level increases the power of a test. So for example, if I had a significance level that was smaller at 0.01 and I increased it to 0.05, I'm more likely to reject that false null null hypothesis. Okay, and then minimizing type 1 and type 2 errors. The law of large numbers dictates that the number of trials increases, the sample result will approach the true value. Therefore, increasing the sample size of a test will more likely detect a true H0 and a false H0. So this actually results in a reduction of both of our errors, type 1 and type 2 errors. So increasing our number of trials is always a good idea. All right, and that is it for today's lesson.